Very good evening, my friends and colleagues. I am going to speak today on stress, strain, and mechanical power, and specifically focusing on the pediatric intensivist perspective. We will be having a brief overview of ventilator-induced lung injury before actually dwelling into the physiological concepts of stress and strain. Then we will understand mechanical power, and then we will have a brief discussion on limitations of adult research in pediatrics and the current pediatric solutions. The concept of possible harm from invasive mechanical ventilation is not new. As early as in 1745, John Fothergill suggested that mouth-to-mouth inhalation of a victim's lung might be preferable to using a pair of bellows, as the lungs of a man may bear without injury as great a force as another man can exert, which by bellows can not always be determined. So historically, we have known barotraumas in 1970s, and then we knew volutrauma from Drifford study in 1988, then Tremblay's study in 1997, and after Gattinoni's paper on mechanical power, we are now discussing about ergotrauma. This is a schematic presentation of alveolo-capillary interface. So we have this alveolar airspace. This is the epithelial basement membrane. We have the type 1 pneumocytes, and we have endothelial cell lining of the capillary endothelium. These are the alveolar macrophages, and we have the surfactant which is covering the surface of the type 1 pneumocytes. Type 2 pneumocytes are the one which are here. And when there is an acute lung injury in the form of a disruption, inflammation at the alveolar capillary membrane, then we see there is a flooding of the alveoli with the fluid, and there is a denudement of the basement membrane, that is loss of the type 1 pneumocytes, and necrotic type 1 pneumocytes can be seen here. There is inactivated surfactant. There is a thickening of the fluid which is in between the alveolar capillary membrane, which affects the gas exchange, and there is a disruption of the both that alveolar epithelium as well as capillary endothelium, and the influx of the neutrophils from the capillaries to the alveoli and alveoli to the capillaries. Atelectrauma was first identified in the year 1997, where it was found that atelectasis and low FRC will increase the pulmonary vascular resistance and increases the right ventricular afterload. It also promotes inflammation, as shown by Tremblay et al. In 1997 by this classical study, animal study, where they showed that atelectasis increased the inflammatory markers in the lung. Biotrauma is basically a condition where local and systemic inflammatory response occurs as a result of lung injury, leading to cytokine production. So we already saw that there is an increased physiological dead space, decreased lung compliance, and there is adverse effect on the gas exchange, and all these things ultimately lead to excess amount of pro-inflammatory cytokines in the alveoli, which get transmitted from the alveoli to the endothelium, and then from here they can actually travel to the entire body, leading to multi-organ dysfunction and even death. Barotrauma, this term itself can be actually misleading, because the critical variable which leads to air leak is the regional lung overdistension and not the high pressure per se. But regional overdistension is not easy to measure, and hence, as a surrogate, we measure the airway pressures like plateau pressure and positive indicated pressure or mean airway pressure to denote barotrauma. Volutrauma means the excess amount of volume causing lung injury. As early as in 1963, Bendixson in 18 patients after anesthesia showed that if you ventilate at higher tidal volume, there will be less atelectasis, less acidosis, and improved gas exchange. And this led to people ventilating at high tidal volumes of 10 to 15 ml per kg routinely for next 30 years, until in 1988, when this landmark paper came from Driffus, which showed that alveolar edema was only associated with high tidal volume, and the PEEP had some protective effect. And then, of course, we know this landmark paper, which was published in year 2000, the ARTSNet trial, which clearly showed that 6 ml per kg tidal volume was better than 12 ml per kg tidal volume in terms of decreasing mortality and increasing the number of days without ventilation. And from there onwards, everybody started ventilating using 6 ml per kg of tidal volume, assuming that lungs to be something like this. However, as we all know, in ARDS, the lungs can be totally different. As we can see here, hardly there is a normal lung available to take up the tidal volume of 6 ml per kg, and most of the lung is actually atelectatic or collapsed. And if you push 6 ml per kg of tidal volume in this lung can have a lot of deleterious effect, particularly a large volume inside smaller capacity lung will increase the pressure inside the lung. And that's why this landmark paper by Meto et al. Came in 2015, which showed that instead of taking tidal volume to body weight, we should actually titrate tidal volume to available respiratory system compliance. And they called it as driving pressure, which was the ratio of VT, that is tidal volume, to respiratory compliance, and measured at the bedside as P plateau minus PEEP. They showed that if you keep the same positive index respiratory pressure but allow the both plateau pressure as well as driving pressure to rise, then you will see mortality rising. While if you make sure that you titrate your PEEP nicely, even if your plateau pressure is going 28 or above, but if your driving pressure is kept below 15 centimeters of water, you will not see much change in the mortality. However, if you titrate your PEEP in such a way that you maintain your plateau pressure less than 28, as well as driving pressure reducing, making it less than 15 actually. So as the driving pressure is reducing, keeping plateau pressure less than 28 and titrating PEEP properly, you will see that actually mortality going on reducing. Now there are a lot of discussions on all these things, which is not the scope of this paper, this presentation, this talk, but this is the part which is the most important in our understanding of ventilator-induced lung injury. So as we know, driving pressure now is basically titrating tidal volume to available respiratory compliance. And we know respiratory compliance is tidal volume divided by change in pressure, that is plateau pressure minus PEEP. Hence, we can substitute it as VT divided by plateau pressure minus PEEP. And when it is inverted, then VT can get cancelled, and ultimately we'll get driving pressure as plateau pressure minus PEEP. And that's what we see. And at the bedside, we calculate driving pressure as a difference between plateau pressure and PEEP. So if this is a pressure volume loop where there is a PEEP here and there is a plateau pressure here, then the driving pressure is the difference between plateau pressure and minus PEEP, and it determines how much tidal volume we are basically going to generate. So they are all interconnected, and if there is a poor compliance, then you will have to either reduce driving pressure and to reduce the tidal volume. So either if you're on a volume control mode, you reduce tidal volume to reduce driving pressure. If you're on pressure control mode, you reduce the plateau pressure or PIP to make sure that you don't deliver too much of tidal volume, finally maintaining driving pressure in the safe limits. So if you have a situation of like a patient with 6 ml per kg tidal volume, you're delivering and having a PEEP of 8 and plateau pressure of 22, driving pressure is 14. And suppose you applied a higher PEEP of around 12 centimeters of water, suppose, and the plateau pressure is increasing from 22 to 28, which is the harmful threshold, and driving pressure also increasing from 14 to 16, that is 28 minus 12 is 16. That means again it is more than 15, which is harmful. So this means that this lung is not recruitable. When you increase the PEEP, it led to harmful increase in the plateau pressure as well as driving pressure. While if your lung is recruitable, then the same PEEP of 12 will actually result in reduction in the plateau pressure and driving pressure also. So this means this lung is safer and it will tolerate higher PEEP and will benefit from applying PEEP. This is a recruitable lung. Driving pressure is still not validated in pediatric age group. Hence, the safe threshold of 12 to 14 is generally recommended. In normal lungs, it is recommended to keep it below 12 centimeters of water. And in children with pediatric acute respiratory distress syndrome, it is recommended to be kept below 15 centimeters of water. Driving pressure should be monitored considering the underlying respiratory compliance and also the amount of tidal volume to be delivered. So driving pressure is basically meant to titrate your tidal volume above available respiratory compliance. And if you are using driving pressure to titrate PEEP, then you need to always understand what PEEP you are measuring that driving pressure and what is the underlying respiratory compliance and what tidal volume is being delivered. Now, with this background of ventilator-induced lung injury and driving pressure, let us get into the concept of stress and strain. This is a schematic presentation of the lung, and this is the airway pressure. This is the intrapleural pressure between parietal and visceral pleura. Normally, the lungs have a tendency to collapse, and two-thirds of this tendency comes from the surface tension, which is then the alveolar walls, and one-third is because of the elasticity of the lung, picroelastin fiber. chest wall has a tendency to move out, and there is a negative pressure which develops between outwardly moving chest wall and inwardly collapsing lung, leading to a negative intrapleural pressure of around -3 to -4 centimeters of water. Now, the pressure numbers which we see on the screen of the ventilator, that is P peak of P20, or mean airway pressure of 10, or P plateau of to 18 centimeters of water. This airway pressure is basically the pressure which is required to open the lung as well as to elevate the chest wall. So this is not the pressure only needed to open the lung, but it is lungs plus the chest wall. Transpulmonary pressure is actually the pressure which is used only to open the lungs irrespective of the chest wall, and it is measured as the difference between airway pressure, which is displayed on the surface screen of the ventilator, and the pleural pressure. And directly we can't measure pleural pressure, so the airway pressure which is displayed on the ventilator screen, and the pleural pressure, because we can't measure it directly by inserting something in the pleural cavity, we can measure esophageal pressure by inserting an esophageal balloon in the esophagus, and the esophageal pressure can work as a surrogate for pleural pressure. Transpulmonary driving pressure means you have to first calculate transpulmonary pressure at peak inspiration, taking difference between P plat, which is displayed on the screen of the ventilator, minus the pleural pressure at peak inspiration. Then transpulmonary pressure at expiration. That is, you will take the positive index pressure displayed on the ventilator screen and minus the pleural pressure at the end of expiration. And then just like driving pressure, which is P plat minus P, you have a transpulmonary driving pressure, that is transpulmonary pressure at inspiration minus transpulmonary pressure at expiration. This was a landmark study published in 2008 by Chumulo et al. On 80 patients of ARDS, where they actually showed that this airway pressure, which is displayed on the ventilator screen, does not correlate actually with the transpulmonary pressure. For example, if you have a normal chest wall elastance, a normal person with a lung elastance to total elastance ratio of 0.7, and you have a peak airway pressure or plateau pressure of 30 centimeters being displayed on the ventilator screen, then you can see here 25 centimeter out of that 30 is used up in opening the lungs, and only 5 centimeters is used to elevate the chest wall, and your transpulmonary pressure is somewhere around 21 or 24 centimeters of water. However, if you have a problem of poor chest wall elastance like obesity, ascites, chest wall edema, pleural effusion, and you have a P plateau displayed on the screen of the ventilator as 30 centimeters of water, but you can see here only 15 centimeters actually used in expanding the lung, and remaining 15 is wasted in overcoming the poor chest wall elastance, and that's why the transpulmonary pressure will be only around 6 centimeters of water, even though the plateau pressure displayed on the screen is 30 centimeters of water. This is what actually Chimulu et al. Also showed in their paper of 2008, where the 30 centimeters of plateau pressure was actually corresponding to transpulmonary pressure of as low as 10 and as high as 28 centimeters of water. So the stress is basically nothing but the transpulmonary pressure, which we already discussed, airway pressure minus pleural pressure, while strain is the elastic fiber undergoing stretching due to the applied stress, that is the change in the volume compared to the initial volume. This is a schematic presentation of alveolar-capillary membrane interface. This is a capillary endothelium. This is type 4 collagen, and this is alveolar epithelium. So there can be a pressure from inside, as we can see in pulmonary hypertension, or there can be a stretching from outside because of the high pressure or high volume, and all ultimately leading to excess amount of stress and strain on the alveolar-capillary membrane, which can lead to various stages of injury like unfolding of the plasma membrane, intermolecular distancing, lipid trafficking, and finally stress fractures which happen in the alveolar-capillary interface and the interstitium. The studies have shown that at a transpulmonary pressure of around 30, things are still safe, but once you go above 30, like 40 or more than 50, you can see there is a dramatically increased number of breaks happening in the alveolar-capillary membrane interface. So the stress and strain are related with each other. Stress is equal to K multiplied by strain. So strain is tidal volume divided by FRC, that is functional residual capacity. K is the lung specific elastance, which is the pressure required to double the size of the baby lung. That means if K is equal to transpulmonary pressure, that means the VT tidal volume will be equal to the FRC. So basically it is that's how it is defined. And as a situation we can see here, you have a patient who has a certain FRC ventilated at a 6 ml per kg tidal volume, and suppose you put this patient in prone positioning, or you applied a higher PEEP or did a recruitment maneuver, and by that you increased the FRC of this patient, but maintaining the same tidal volume of 6 ml per kg. If you look at it now, the mathematically what you are doing is you are increasing FRC, that is the denominator, and keeping the same tidal volume. So basically you are mathematically reducing the strain, and when you're reducing the strain, the stress will also reduce. So that's how we can explain how lung recruitment helps. So when you recruit the lung by a recruitment maneuver or PEEP, application of a good PEEP, this will reduce the strain and as well as reduction in the stress. Though at zero PEEP, suppose you measure the end expiratory lung volume, that is called FRC, and the tidal volume which is there on the top of the FRC, when you take the ratio of them, that is basically a dynamic strain. And you have a total lung capacity which is roughly 2.5 to 3 times the FRC. And when you apply a certain PEEP, then you are basically introducing a PEEP volume in the system, and you have an end expiratory volume now, which is PEEP volume plus this FRC. While when you want to calculate global strain, that will be tidal volume plus PEEP volume divided by FRC. That will be the global strain. And you can see the quality of a good PEEP, as we already saw. If it causes a good alveolar recruitment, it will reduce the strain, it will reduce the stress. And at the same time, you can see that the end inspiratory lung volume, that is the end of the volume of tidal volume, is still safely away from the total lung capacity. So it is safe and win-win situation. Studies have shown that when the transpiratory pressure is reaching around 24 centimeters of water, then you are actually in the danger zone of the strain of above 1.5, where barotrauma features are seen in histopathology. So this around 24 centimeters of water of transpiratory pressure will correspond to plateau pressure displayed on the mechanical ventilator of around 28 or 30 centimeters of water. If the chest wall elastance is normal, there is no obesity, ascites, or chest wall edema. So if you don't have a facility of esophageal pressure monitoring, you can't measure the exact transpulmonary pressure by taking airway pressure minus pleural pressure. What you can do is, if the chest wall elastance is normal, there is no pleural effusion, obesity, or ascites, you just keep your plateau pressure less than 28 to 30 centimeters of water, and most of the times your transpulmonary pressure will be less than 24, and hence your strain will be less than 1.5, and you will be in the safe zone. This is what it says. Proti et al. In the study on pigs showed that when you are reaching the upper limit of your total lung capacity, there is increased risk of ventilator lung injury. So that means the normal PEEP already we discussed as characteristics of a good healthy PEEP, where your end inspiratory lung volume is safely away from total lung capacity. But if you have an excess amount of the PEEP in the system, then you can see here the end inspiratory lung volume is touching the total lung capacity now. So if this patient is breathing, suppose at a rate of 30 per minute, 30 times in every minute you are hitting the total lung capacity, which will increase the risk of volume trauma. So an optimally applied PEEP will prevent ventilator-induced lung injury only when the tidal volume is low. If tidal volume is also high, it is ultimately going to cause volume trauma. Higher PEEP can be harmful when the global strain is high due to excess amount of PEEP volume pushing the lungs into total lung capacity. Thus, as we saw now, VILI can be minimized by optimizing the strain, that is optimizing the positive induction pressure and tidal volume against the available FRC, optimizing the lung stress, as already we saw, transpulmonary, inspiratory and expiratory pressures and transpulmonary driving pressure, and an optimal respiratory rate and gas flow. So when we combine all this, unify this pressure and non-pressure parameters, and then multiply them by respiratory rate to express them in joules per minute, then we get this particular thing called mechanical power, which is the last part of my talk today. So in 2016, Gettinoni et al. Presented this paper and came up with this equation of mechanical power for volume control mode called comprehensive equation. So this equation has an elastic component, it is a resistive component, and it has got a static component. This is basically a modification of a equation of motion. And when these things are multiplied by respiratory rate, then you get mechanical power, which is expressed in joules per minute. And the term ergotrauma basically means mechanical energy delivered to the respiratory system and causing ventilator-induced lung injury. The advantage of a mathematical description of mechanical power is that it enables quantification of the relative contribution of its different components like tidal volume, respiratory rate, airway pressures, IE ratio, gas flow, etc. And it anticipates the effect of their change. For example, as per from the Gattinonis equation, if we see tidal volume, gas flow, and driving pressure have got maximum impact and followed by respiratory rate and least impact with PEEP. And how does it help us? For example, the ARDSNet study had recommended using high PEEP and low tidal volume. So what we are trying to do by that strategy is you are reducing the tidal volume, which has got the maximum impact on mechanical power. And because tidal volume, if you reduce, it will result in atelectasis. You apply higher PEEP to prevent atelectasis. And by that, you are actually not increasing mechanical power much because impact of PEEP on mechanical power is far less as compared to impact of tidal volume. So this is how you can explain for this equation how high PEEP, low tidal volume strategy actually works. The rate in duration of mechanical power is important. This is a study in rats again, which was done. A very interesting study. What they did was they applied a 6 ml per kg of tidal volume in control group throughout over 2 hours. And there were three other situations: no adaptation, short adaptation, and long adaptation. No adaptation, they applied 6 ml per kg of tidal volume for 1 hour and then suddenly increased to 22 ml per kg. In short adaptation, they had a 6 ml per kg tidal volume for 30 minutes and then increased over next 30 minutes and then maintained at 22 ml per kg. And there was a long adaptation where throughout the 24 first 1 hour tidal volume was increased and then maintained for at 22 ml per kg in the last 1 hour. And they found that the short adaptation period was the only condition where you had least lung injury, least amount of release of inflammatory cytokines, while when you applied a short adaptation time, then there was less impact and less release of inflammatory markers. So duration over which the energy is released is also very important. And this is another study by Proti et al. Where they showed that the increasing strain rate resulted in threefold increase in the prevalence of pulmonary edema. So it is not just the strain, even the strain which is considered as safe at low rates was harmful when it is applied at higher respiratory rates. So this means that lung injury is more at higher rates and longer duration. This means the energy which is used to distend the lungs, to move the gas, and to keep the lung alveoli open will depend upon the respiratory rate. And each component will have its impact only at higher rates. There are various methods of calculating mechanical power. First is geometric method, where area under pressure and a volume is taken and multiplied by respiratory rate. That algorithm is present in some ventilators like Hamilton and Mindray ventilator. Then there are two equations, surrogate equations and comprehensive equations, by which mechanical power can be calculated in volume control as well as pressure control mode. So in volume control, we have Gattinonis comprehensive equation, which was published in 2016. After that, simplified Gattinonis equation also came. So these are the comprehensive equations. Comprehensive equations mean you need to stand at the bedside, apply inspiratory hold, and measure the blood pressure. So you need to be at the bedside for comprehensive equation. Then a surrogate equation is introduced, like Giosa's equation for volume control mode. Surrogate equations don't need standing at the bedside, applying the blood pressure, applying the inspiratory hold for measuring the blood pressure. So even retrospectively from the ventilator charts, you can take the data and calculate mechanical power using surrogate equations. For pressure control mode, comprehensive equations are Van der Meijden equation, Becker's equation, and there is one more called Tinkle et al.'s equation, which is not mentioned in this particular table. And the surrogate equation is the simplified Becker's equation, which is the surrogate equation in pressure control mode. Studies have found that in adults, 12 to 14 joules was associated with the significant probability of mortality if the mechanical power is higher than 12 joules. And in another study, which is very famous study by Serpanito, cutoff value of around 17 joules per minute was found to be harmful, above which if it is mechanical power is delivered, it is harmful. But it is very important to understand that children are different from adults, and we can't simply extrapolate the findings of adult age group research into children. In children, the chest wall elastance is very low in younger age group. That is, chest wall compliance is very high up to first 1 to 2 years of age, and only after 2 to 3 years of age, the chest wall elastance will be like the chest wall will be stiffer and increase to the point of the chest wall, and the lung are nearly equally compliant. And this is important because if the chest wall is more compliant, it will keep falling on the lung, and the end expiratory lung volume will be lower. Infants augment their EELV in the respiratory distress by grunting, and the chest wall stiffness increases by the age of 3 years of age, and this allows the child to maintain the ELV passively. In young infants, the mechanical ventilation, which causes inflammation in the alveolar capillary interface, will generate more elastin fiber as compared to collagen fiber, which happens in adults. So more risk of injury in adults compared to children. And also studies have shown that higher tidal volume generates more surfactant production in children, which is basically protection against the inflammation. This was a famous study by Copland et al. In newborn rats, and they found that newborn rats were significantly less susceptible compared to adult rats in terms of developing inflammatory cytokines in the lung. And also, the ratio of total lung capacity to body weight is significantly larger in infants as compared to the adult rats, and hence the stress and strain will differ in smaller children, particularly less than 3 years of age, as compared to older children. This was one more very important study by Cornick et al., where they showed that at the end of inspiration, the alveoli size appear more uniform in infants as compared to adult, and hence the utility of positive end expiratory pressure or recruitment maneuvers may differ in infants compared to adults, and thus we should be careful while extrapolating literature from the adult age group. Now, the tidal volume also, it's very unclear whether high tidal volume is really harmful in children as compared to adults. In adults, we already saw there are so many studies which have shown that high tidal volume is harmful. But in children, these are the list of the studies. These are the 5 studies which actually showed that high tidal volume may not be harmful, and these are the 4 studies which showed that high tidal volume may be harmful in children. So still, we are not clear whether we can really take the data from the adult studies and extrapolate into children. Similarly, mechanical power behaves differently in children. And if you look at the mechanical power equation by Gattinoni et al., there are 2 important components of this equation: respiratory rate and tidal volume, and they change with age. As the child increases with age, respiratory rate falls and tidal volume increases. And thus, the mechanical power goes on increasing as the age increases. Thus, the Serpent-Nato, how they gave a cutoff value of around 17 joules per minute as harmful in adult age group, it is not possible to give that kind of cutoff in children, because normally itself mechanical power goes on changing in children. This was a study which was published in year 2020 by Dr. Martin Neber and his team, where they removed the respiratory rate from the equation of mechanical power, and they had normalized the tidal volume to body weight, and presented this equation as mechanical energy. But as we can see, they found that a mechanical energy does not change with age, or changes minimally with age. But the problem is the respiratory rate, as we already saw, is such an important and key component of mechanical power, has been removed from this equation. Doesn't look like a very good solution to the problem. Mechanical power can be normalized to body weight or respiratory compliance. This was the study by Coppola et al., where they found that after normalizing the mechanical power to respiratory compliance, the MP normalized to respiratory system compliance was independent associated with mortality and adjusting for the age and other things. This was our study, which was published in January 2024, where we analyzed the impact of normalized mechanical power and mechanical energy on the outcome of ARDS patient. And we found that only MP normalized respiratory compliance at both first 4 hours and 24 hours, but not the normal mechanical power or mechanical power normal as to body weight or mechanical energy was significantly correlated with ventilator free days at 28 days. So after thus lung can be protected by decreasing the inspiratory as well as expiratory mechanical power, ensuring the optimum rates and duration, and trying to increase the lung homogeneity. Lung homogeneity also is a very important point, because as we have seen already in ARDS, lung can have an area where you can have a good gas exchange, that is called as a baby lung. You can have an intermediate zone, which is also called as a recruitable lung, where if you apply a PEEP, and if that PEEP can lead to recruitment of the alveoli, it will reduce the stress and strain, as we already saw in previous slides, and it will be It will keep your end inspiratory lung volume safely away from total lung capacity, and you have all the benefits of a good PEEP. And then you have a last phase, non-recruitable part of lung, where either the alveoli will never open no matter what PEEP you apply, or they may open at a very high PEEP, and that high PEEP can be harmful because then the volume will be too high, or your total lung capacity will be hitting. So these are the three parts in the lung, and even homogeneity promotes the development of more stress risers. And the studies have shown that at the junction of the open alveoli and the collapsed alveoli, the pressures can go as high as 140 centimeters of water when the transpulmonary pressure is only 30 centimeters of water. So on the ventilator screen, you may see a pleury pressure of 28 or 30, but the pressure at the interface between the collapsed alveoli and open alveoli can be as high as 140 centimeters of water. And that is why it is important to remove these atelectatic areas and apply a good recruitment maneuver or prone positioning, something like that, to make sure that we have less and less of stress raisers. These are called stress raisers, because if you have a recruitable lung and you can open up this alveoli, then the mechanical power imparted to those lungs will be much less as compared to a lung which has only two areas, that is baby lung and completely atelectatic lung, and very small intermediate zone where recruitment is possible. So in such situation, impact of mechanical power will be more harmful. So the best available maneuver is prone positioning. Like in this presentation, we can see in supine positioning, a lot of atelectatic alveoli and dorsal part, and after giving prone positioning for 16 to 18 hours, you can see all the atelectatic alveoli are almost open and well aerated, looking well aerated. In another example, you can see completely atelectatic alveoli at the dorsal part in severe ARDS at a PEEP of 5. And when you increase the PEEP to 15 centimeters of water, still you can see hardly alveoli opening. So proning is actually more efficient than even applying very high PEEPs to open the alveoli and create alveolar recruitment. This was one study by Bhushan Katira, which was published in 2021 from Toronto, where they showed then in prone positioning, the pleural pressures are higher, and thus the transpleural pressure decreases and at each PEEP level. So the natural history of ARDS itself is in such a way that all this inflammation, edema, lung weight, and compression atelectasis, as the ventilation goes on, they will amplify as the mechanical power goes on increasing. So mechanical power may increase because of these things worsening, or higher mechanical power can worsen these things, whatever it is. And hence, when you are applying mechanical power, you need to see whether a lung is recruitable or not recruitable. And if your lung is recruitable, you can apply recruitment maneuvers like proning or recruitment maneuver, and you will see that you can achieve better lung homogeneity. You will reduce the stress raisers, and you will reduce the driving pressure and pleury pressure to deliver the same tidal volume and less ventilator-induced lung injury. If it is not recruitable lung, then recruitment maneuver or proning may not actually change lung inhomogeneity, and the driving pressure may remain high, pleury pressure may remain high to deliver the same tidal volume, leading to more ventilator-induced lung injury. Thus, the impact of mechanical power will depend upon underlying lung condition and systemic illness, and that's how we can explain how driving pressure less than 15 centimeters of water, or how the low tidal volume, high PEEP helps us, and how the prone positioning helps us. And of course, neuromuscular blockade in first 24 to 48 hours in critical phase is also important. So once you diagnose parts, you need to apply lung protective ventilator strategies like keeping the pleury pressure less than 28 and tidal volume of around 4 to 8 ml per kg, that is low tidal volume and high PEEP strategy. Optimize your PEEP, and then you see if you are able to maintain your pleury pressure less than 28, that means you're in a good comfortable zone. Continue your ventilatory monitoring, and displayed just monitor your airway pressures, which are displayed on the ventilator screen. If your pleury pressure is more than 28, then you need to ask whether you have any suspicion of poor chest wall compliance, like obesity, pleural effusion, chest wall deformities, intra-abdominal hypertension, etc. If yes, then of course you need to have a transpulmonary pressure monitoring for proper transpulmonary pressures and guided treatment. And if you don't have suspicion of abnormal chest wall elastance, there is no obesity, ascites, pleural effusion, then you can simply, there is no need of transpulmonary pressure monitoring. You can just monitor the pressures displayed on the ventilator screen and take your decisions. There are other things also, like monitoring strain, which is beyond the scope of this talk, so I will not touch that. So it is likely that in some patients, ventilator-induced lung injury is totally unavoidable because that baby lung size may be very small, and then there is nothing else can be done. The impossibility of safe ventilation will, in such situations, will be the rationale for using extracorporeal oxygenation, that is ECMO. Thank you very much.